No, he just doesn't. I don't know what he looks. There's nothing outside. He's looking at a window and there's nothing out there. So I don't know. Okay, so let's look at 2.2. So which one would you like to go over, Alexandra?
I don't know. I think there's something going on with the way that I'm multiplying the cases or something. Like, for example, number one, A and B, my solution was twice the amount. So I think I realized that I was just not dividing out two for the socks to make a pair. So maybe
Yeah.
not number one, but number three maybe would be good.
Number 3.
Yeah, thank you.
So let's look at number 3. It says a student has to sell 2 books from a collection of 6 math, 7 science, and 4 economics books. How many choices are possible if, part A, both books are to be on the same subject, part B, the books are to be on different subjects? Okay. Let's do part A first. So what does part A ask? Let me turn this over here. All right, so this is 2.2, number 3. So we have 6 math books. We got 7 science books. And we got 4 econ books. And I want to figure out how many ways can I choose 2 of them. And for part A, I want 2 of the books to be of the same subject. 2 of the books, same subject. So Alexandra, how did you go about doing this?
Sure. Let me just go back. I was checking to see which other ones I was getting wrong while you were setting it up, but I approached it by, so there's 6 math, 7 science, 4 economics. So number A, I did 6 times 5 plus 7 times 6 plus 4 times 3. So I just did like, I guess a permutation of each.
Yeah.
Yeah.
I think that's all. That's the only mistake you did.
Okay.
Because the order doesn't matter, you shouldn't be considering it as a permutation.
Oh, it's a combination.
It's a combination. So to edit your approach, all you have to do is divide by 2 for every single product. But if you don't see that, so you can think of this is under casework, isn't it?
Yeah.
Yeah. So the idea is, what's case number 1? The first case is that they're all math books. So only math. Well, if I have 6 to choose from and I only choose 2 of them, what's the number of ways to do that? 6 choose 2. And what is 6 choose 2? Isn't it 6 factorial over 4 factorial times 2 factorial? Isn't it 6 times 5 times 4 factorial over 4 factorial times 2 factorial? Do you see where the 4s cancel here, the 4 factorials, and you're left with exactly what you just said?
Yeah.
6 times 5, but that 2 factorial is what gets rid of the repeated case, where if you have one on linear algebra and the other one on probability, the same thing as saying probability first, then linear algebra. That's where the 2 factorial comes into play. So you're left with 15 ways. And then you just build yourself up from there. So case 2, hey, what if they're not math, neither math nor econ, but only science? And then it's the same idea, right? So this becomes 7 times 6 over 2, which is 42 over 2, which is 21. There's 21 ways for case 2. And then case 3, there's only econ. And so there should be 4 choose 2 ways, which is 6. And of course, these are mutually exclusive cases. That's the very reason why we're talking about cases, because they're not overlapping. You either have only math, only science, only econ. So because they're mutually exclusive, events, we can add these up together, right? So the total number of ways is 15 plus 21 plus 6, which would be what? 15 plus 27, which would give you a grand total of 42 ways.
Okay, that makes sense.
And yeah. And then how would you get part B?
Sorry.
Same thing, just choose one for each. What do you mean by choose one for each? So part B is actually very much, you can treat it the same way with casework as you did in part A. So you can say, what if they're different? They have to be different, correct? So I must have a math and a science combination. Then I must have a science and an econ. So I must have one math, one science, or I have one science, one econ, or I have one math and one econ. So those are the three cases, right? And you do that sum, right? And then you get whatever that number is, right? And what is that number when you add those up? So 7 times 6, right? Plus 4 times 7 times 4 times 6. What do you get?
40.
Can you sum
I
them up?
mean, 36.
Really? 7 times 6 is 42. But then 4 times 7 is 28. And then 4 times 6 is 24. So when you add 42 plus 28 plus 24, you get 94. That's right. So that should be the answer. And that's if you view it from that perspective, right? When you have one math, one science, one econ, right? So I'm just gonna go through it. I don't want to cut any
Can you
corners.
also, do you have to do it by casework? Can you do it by
No.
the complement? So you subtract 42 from the total number of ways? Because that's how I did it.
You should be teaching this. Yes.
Okay.
Yes, Alexandra. That's right. That's exactly, I was going to segue into this. Yeah, I know my buildups are a little bit long, but I was going to segue. I'm like, yeah, you can view it that way with the cases. Perfectly fine. You get the same answer. Or you can say, wait a minute, if I found a number of ways for them to be the same, I can figure out the total number of ways of just selecting two books out of what? This would be a total of what?
136.
17 books, right?
Oh, yeah.
I got a total of 17 books. I don't care what they are for a moment. How many ways can I select 17 books? At 17, choose 2 ways, which is 136 different ways. Of 42 of them, 42 of these 136 ways is if you have all the same subject. The complement of having the same subject is you don't have the same subject. You have different subjects. So that's why it makes sense to subtract 136 from 42, and you also get 94. So either way, if you viewed it as a casework problem, right? If you viewed it as a casework, so if this was casework, this would be the answer, okay? I just want to show this for those of you who thought of casework. So this would be 7 choose 1 multiplied by 6 choose 1 plus, next one is what? 7 choose 1 multiplied by 4 choose 1 plus 4 choose 1 multiplied by 6 choose 1. What does this represent here? 7 choose 1 represents 1 science and 1 math. That's case 1. Case 2 is if you have 1 science and 1 econ. That's case 2. And then case 3 would be 1 econ and 1 math. That's the only other possibility. That's case 3. And when you add these numbers up, you get 94. Or you can think of it as a complementary version where you say, wait a minute, I already figured out the complement of having different subjects, which is the same subject. So this would be 17 choose 2 minus 42. This is the total number of ways. And this is the total number of ways for same subject. Which would mean that if I subtract 136 minus 42, I get 94. And this is the total number of ways for different subjects. So if you see the complementary version of this, this is a very good sign, which means that you're thinking from a complementary perspective, which is actually very useful, as you can tell. Can we do question 4 on the same section? Okay, so question number 4 for casework, it says, how many 3-digit numbers have a first digit which triples the final digit? This should be fairly quick. So we have, what do we have? This is 2.2 number 4. So I want a 3-digit number. So I'm going to use this idea of having the slats, right? And the first digit, well, first of all, this is the first digit. This is the second digit. This is the third digit. And I want that the third digit, I want to have a first digit, which is triple the final digit. So I want this number here to be 3 times as big as this. What does that mean? This number inside here, this number, I can have any number, any digit. So how many digits are there to choose from? 10. This second digit has no restriction. So I could be any of the 10 digits, right? 0 through 9. 0, 1, 2, 3, all the way to 9. Now, what can the third digit be? The third digit is related to the first digit. The first digit has to be 3 times as big as the third digit. So for example, 1 would work, right? If this was a 1, then this would have to be a 3. What about the next number? 2. If this were a 2, then this would have to be 3 times as big, right? This would be a 6. If this last digit was a 3, then this would be 3 times as big. This would be a 9. But the moment we go to 4, it doesn't work. What's 3 times 4? 12. We can't have a digit that's 2 digits. You can't have 2 digits squeezing into a place where you only could fit 1 digit. So there's only 3 possibilities for the third digit. The moment we select one of these 3 digits, there's only one way to selecting this last digit, because this last digit is dependent upon what this digit is. So I only have one way. Once I select that last digit, I only have one way to select the first digit. So there's a total of 30 when you multiply. There's a total of 30 different integers who are 3 digits, whose first digit is 3 times the last digit. Any questions about number 4? No questions. Excellent. No problem. Any other questions throughout any of these numerous problems that you have here? So much to go through. Okay, 3.1, number 3. So 3.1, let's see what 3.1 is. 3.1, number 3. Okay, no problem. Let's do that. So these are typical counting questions. 3.1, number 3 is very typical. The subcommittee stuff, yeah. So we have a Senate committee, and it consists of 5 Republicans, 6 Democrats, and 2 independents. And it asks a subcommittee of 3 members is randomly chosen. What is the probability that the subcommittee consists of 3 Republicans? So I want the probability subcommittee spell committee wrong. Subcommittee has 3 Republicans. So how do you find the probability? Well, first I need to figure out what's the total number of ways of selecting 3 members into a committee, right? The bottom denominator is not necessarily what we desire, but what's the total number of outcomes for this particular experiment. Are we getting this lecture recording or notes today? Of course, Chaitanya, this is how I do things. I record and I upload. So for your previous the other class that you're taking, it's up right now, so you should be able to access it. And the same thing happens for this class. I'm going to record, and then all this stuff will be uploaded as well on Blackboard, so you guys can be able to see it, retrieve it, and go over it. So Mir says 5 choose 3 over 13 choose 3. That's right, because what's the total number? What's the total number of books? I was gonna say books. So you can choose books, you can talk about cars, you can make this problem in so many different ways, but people like using political parties for this for some reason. So then here we have 13 different people and we're choosing 3 of them. That's the total number of ways of selecting 3 people. But my particular desired outcome is that 3 of them are not Republican, but yeah, 3 of them are Republican. How many Republicans do I have to choose from? 5. So I choose 3 of them. So this is literally what I compute. And you can use this using your calculator. 5 choose 3 divided by 13 choose 3. Why can't you do 3 over 3? 3 is for part A. Okay. 3 choose 13. 3 over 13, pardon me.
Like just multiplying. So there's 13 total, right? So you have, you choose 3 Republicans and you choose 2 Republicans, but you've already chosen one. So you have their denominator goes down to 12. And then you choose 1 more Republican for the 3rd place. And so you have 1 choice over 11, which is left because you've already chosen 2 spaces. So it's like you have 3, it's almost like you have 3 spots. It's almost like the 52 card deck.
It's
like
almost, yes.
So I don't know why doesn't this make sense?
Because what are you doing? You're doing slots, right? You're saying the first slot, second slot, third slot. And
Right.
you're saying I'm choosing only, so you're saying that the number up here is the number of Republicans I have, right? I'm choosing 3 of them. But then I also have 13 ways to choose it overall.
Right.
And then over 12, I have 2 of them.
Because you've chosen 1.
Yeah.
Like I was thinking of the 52 card deck, and then, you have like different suits, and then you're choosing 1 and then another one and another one. You just multiply across.
Mm-hmm. So there's something about this, right? You see how it becomes kind of tricky? Because there's inherently here, you're dealing with order.
Oh, so, with my example is order?
Yeah.
Oh, you're right. Okay.
There's overcounting immediately because you're saying there's 3 ways to choose. So you have 6 ways, but 5 choose 3. But I want to just continue with this, and then hopefully it can give us some insight as to why this product is not necessarily complete or correct. Okay. So let me just keep that in mind. But that's a great question though, because sometimes it's a very typical question to ask, like, why don't we look at it from this perspective? Why do we look at it from that perspective? So the reason why we use combinations for a fact is because the order of the selection does not really matter, right? I just want 3 Republicans. So how many ways is that? So let me just write it out how this would look as if you were to compute it. So that should give you some insight. I would have this, right? And then this would be 13 factorial over, what is it? 10 factorial times 3 factorial, right? Now, if I look at this a little bit carefully, this would be 5 times 4 times 3 factorial over 3 factorial times 2 factorial, right? The 3 factorials cancel. And then this would be 13 times 12 times 11. You see how these numbers appear? They appear again, 13, 12, 11. So that's okay. That makes sense, but hold on. Then this is times 10 factorial. 10 factorials cancel. There's 3 times 2 factorial. So then this becomes, I'm not subtracting, I'm not dividing this out yet, this part yet. So this becomes 5 times 4 all over, sorry, this is 2 factorial, and then I'm multiplying by the reciprocal, right? So this is 3 times 2 times 1 over 13 times 12 times 11. Now these 2's cancel out. So really what I have is 5 times 4 times 3 all over 13 times 12 times 11. And these numbers here cancel out here. So I'm left with 5 over 143. So this is the probability. Sorry, 1, 5. Now, why doesn't this work? Well, inherently, you're dealing with order. The order of, you're saying that the first position in the subcommittee is 3. There's 3 choices for that. The second position in the subcommittee, there's 2 of them. So this idea, immediately you're dealing with order.
So I screwed up in that I put 3, 2, 1, which is the number of slots. But what I meant to put was 5 Republicans, 4 Republicans, and 3 Republicans, which is what you ended up with. And that would have been the same. That was what I was thinking, but I executed it wrong. So I'm glad at least my thinking was correct.
Right. So yeah, you're right. You could have done it your way. It's just that you see how this is the proper way to look at it. But do you see how the numbers here cancel out, and you're able to see, oh, that's what I should have done, because you're looking at this only particularly, right? You're only seeing, oh, 3 Republicans, but you have originally you had 5 of them.
Yeah, exactly. Okay, thank you.
Okay. So, but that's a good idea. Still good. You had a good idea. Okay, so that's part A for number what is this, number 3? And now part B. What does part B say? Part B says consists of 1 Republican, 1 Democrat, and 1 independent. So do we see what we're supposed to do for this one? We can do your way, Alexandra. So it should be the same, right? Like, I like your way too, because that's more intuitive. The other way is more formulaic. You don't really think about necessarily the selection, but you can also say, oh, I have, how many Republicans do I have? I got 5 to choose from. How many Democrats? I got 6, right? And then how many independents? I got 2. And then this becomes 13, 12, 11, which is the same thing as saying what? 5 choose 1 times 6 choose 1 times 2 choose 1 all over 13 choose 3. It's going to be the same. It's going to be the same thing. And so these go away, and I'm left with wait, what is it, 7? I think I messed up somewhere with this. Yeah, just something went wrong with this. Hold on. I am missing. We took 1 from, yeah. So let me look at this first. This is 5 times 6 times 2, and this would be what? This would be 13 factorial over 10 factorial and 3 factorial. And we already know what this is going to appear like, right? We already know that this would be This looks like something like this. So it'll be 13 times 12 times 11. So 5 times 6 times 2 over 13 times 12 times 11 over 3 times 2 times 1, which would be 5 times 6 times 2 over, this is 3 factorial over 13 times 12 times 11. And do you see why there's a 3 factorial here? Do you see why? Do you see why we need it? Does anybody see why or no? No, okay. It's because I say, you know why? It's because I said this. I said this is Republican, this must be Republican, this must be a Democrat, and this must be an independent. That's how we got this number. But why does the first one have to be a Republican? So the reason why there's a problem with this approach this way is because the bottom numbers account for the order differences. The top number doesn't. The top number only accounts for the way if I choose a Republican first, then a Democrat, then an independent. But in this number, there's 3 factorial ways to permute them. You see that? So there must be a 3 factorial attached to it. So you have to be very perceptive. This is something that it's almost a very nuanced, right? It's very easy to subtle, it's very subtle, and it's very easy to look over. And so then it's very easy to confuse yourself. You're like, wait, no, but I can think of it this way. I could do, but you have to be careful. So, well, Alexander, that's exactly why you don't divide. You're multiplying. Why? Well, not just because it appears because you have to multiply given the formula behind this. It's because if we look at it in this direction, right, in this manner, so forget about this for now. Look at it from this perspective. The way I set this out to be, the way I created these slots inherently was by an order, right? I said the first slot represents the number of ways to select a Republican, 6 ways to select a Democrat, and 2 ways to select an independent. That makes sense. But why do I make this a Republican first, then a Democrat, then an independent? Shouldn't I also include the fact that this is the Democrat, Republican, independent, or a Democrat, independent, Republican? Because that's exactly what I'm doing here. The moment I do 13 times 12 times 11, I'm treating it as every permutation, every ordering of a Republican, Democrat, every one of those counts. But up here, I'm only suggesting that Republican, Democrat, independent, that should be the order. But I care about the order. So this is not complete. This statement here is not complete. Because here I'm treating this as Republican, Democrat, independent. And here I'm treating them as Republican, Democrat, independent, dependent, Republican, independent, and all those different variations. So for every single one of these combinations that I have up here, for every single one of these orderings that I have 3 factorial ways to permute them. So that is why I have to multiply by 3 factorial. No, the answer shouldn't be 120 over 143. It should be 30. It should be because this comes out, this cancels out. You see that? The 2 and the 6 cancel out to 12. 5 times 6 is 30. Over 13 times 11 is 143. So the answer should be 30 over 143. So all I'm saying is just be careful, be mindful. This is a great question to look at and to see how it's very simple to kind of, lose your way when you look at it from this perspective. You have to be careful with this perspective. With the combinations, you kind of just like forget a bit about all these like smaller details. But if you look at it from this perspective, you have to consider the 3 factorial ways of permuting this. Okay. Okay. Any questions about this? Any other questions you may have? Anything else, guys? Girls, women, people, my people. Number 3 point, okay. 3.2, number 2, A, B, and C. All right. So 3.2, number 2. Yay, we roll a fair six-sided die. So we roll a fair six-sided die. And we do this 5 times. It says what, and we get an odd number in exactly 4 of the 5 rolls. What is the probability that we get an odd number? Probability we get an odd number in exactly 4 of 5 rolls. Well, if we have a six-sided die, right, we're dealing with 1, 2, 3, 4, 5, 6 being on the die. So what's the probability of rolling an odd number? Half, right? That makes sense. So probability of rolling an even number is also half. So look at the slots thing. So this is where you can look at the slot method, right? Like the different blank spaces. So this is the first roll, so on and so forth. Second roll, right? Third roll, fifth roll. Now, what can happen? I can have odd, 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 even. What's the probability of this particular outcome occurring? Well, I have 1/2 for this guy times a half times a half times a half times a half. This is what? 1/2 to the 5th power, which is what? 1/32. But of course, this is not the only configuration where this gives me 4 out of the 5 rolls being odd. I can also have what? Even, odd, 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 odd. Right? Isn't this also possible? So isn't this probability the same thing? 1/32? 4 odds. That's exactly what I just said. Exactly 4 odds. I have exactly 4 odds. 1, 2, 3, 4. 1, 2, 3, 4. No, it says exactly. Exactly means only 4. It can't be more than 4. It can't be less. It's exactly 4. And so that means that I can do this, right? But isn't there another possibility? Exactly. We can choose even. We can choose even. We can choose even being the last number, even being the fourth number, even being the third number, even being the second number, or even being the first number. So Alexandra, no, it's not times 4 factorial. It's just times 5. It's not even 5 factorial. You don't even need to do the factorial because there's only 5 configurations where I have exactly 4 out of 5 being odd numbers. Because I don't care so much. So I don't care so much what odd number it is. I just care that it's odd. So this could be 1, 3, and 5, right? This could be 1, 3, and 5. I have 3 choices for each of these. I don't even worry about that. I just care what's the fact of getting odd number. It's a half. Great. So there's 5 ways of doing this. There's 5 outcomes that I want. Each outcome is 1/32 chance. So if each outcome is 1 out of 32 chance, right? And for example, this outcome is not the same as this outcome, right? They're mutually exclusive. They can't be the same. So if this probability is 1/32, this probability is 1/32. What's the total probability of all of these different 5 outcomes having the same probability? What is that? That's 132 times plus 132 plus 132 plus 132. That's 5 times. So it's 5 over 132. Mir, you have a question? 32, pardon.
Yeah, can we just find all the ways in which we get 4 odd numbers and then subtract from that all the ways in which we can get 5 odd numbers?
Why do you want to subtract them?
That way I have the number of ways in which I have just 4.
So you would, wait, what would you do again? You would count what?
To find the numbers, to find the number of ways that I can have exactly 4, I would get the number of ways I can get 4 odd numbers, and then subtract from that the number of ways I can get 5 odd numbers.
But aren't you? No problem, Rebecca. Have a good day. Aren't you? You're looking for the number of way, the probability of selecting 4 of the 5 rolls rolling on an odd number. But you're telling me you're gonna find that by finding the ways of getting 4 odd numbers. And then
And
subtracting
subtract
it.
from that, because, right,
I feel like you're you're trying to find something based upon what you're trying to find. Like you're trying to find the ways of getting an odd number 4 times, and you're trying to find that by finding the ways of getting 4 odd numbers.
and then also subtracting from it the ways I can get 5 odd numbers. That way I have only the exactly 4, and
I
then
know. I think I know what you're trying to do, but what I'm saying is you don't. I think what you meant to say is, which is I'm just gonna say it straight up. It's a more roundabout way of going about it. I think what you meant to say is I'm gonna find all the number of ways of getting less than 4 odd numbers. So how many ways can I get 0 odd numbers, 1 odd number, 2 odd numbers, 3 odd numbers, and subtract them from the number of ways of selecting 5 odd numbers, and then that would give you the number of ways of exactly 4 odd numbers. I can see why you would do that, but it's just longer. This is the most direct way, because there's only, so whenever you see the word exact, you don't have to worry so much about it's complementary counting. Complementary counting comes up when you have the words at least or at most, because then you're like, wait, I don't want to count. Like if this was saying, if this said this, find the probability of having an odd number in at most 4 of the 5 rolls, then you would have to consider of getting 4 of the 5 rolls being odd, 3 of the 5 rolls being odd, 2 of the 5 rolls being odd, 1 of the 5 rolls being odd, 0 of the 5 rolls being odd. That's a lot of work. So instead of doing that, I'm just going to do the total number of ways, subtract it from the ways of getting 5 odd numbers, and then I get the complement, which is what I'm looking for. See? But for this problem, it's just exactly 4. So you don't have to worry about any of the other scenarios, just 4 of them. And this is the most direct way.
Thank you.
No problem. So that's part A. Now, what is part B? What does part B ask? It says we get a 1 or a 2 in exactly 3 of the 5 rolls. So again, we get a 1 or a 2 in exactly 3 of the 5 rolls. We can say, look, what is A? A is the event of rolling a 1 or a 2. What's the probability of that happening? Anybody? What's the probability of rolling a 1 or a 2 on a 6-sided die? 2, 6, which is a third, right? What's the probability of not rolling a 1 or a 2? So the complement. Isn't it just 2/3? Right? The complement is not 1 or a 2. And I want of the 5 rolls, so 1, 2, 3, 4, 5. I want of these 5, I want 3 of them to be a 1 or a 2. I'm just going to call that event A, right? So I want event A to occur 3 times. So this could happen. This could be A. This could be it. And then this will be what? A complement, A complement. That's one way. What's the probability of this happening? Well, what's the probability of me rolling an A? A third. If I roll the next die, right? It's independent of the previous die. That's why I multiply. This is 1/3 again. What's the probability of me getting not a 1 or a 2? 2/3 times 1/3 times 2/3. This is a total of what? 4 over 3 to the 5th power, which is 4 out of 253. No, sorry, 243. Right? But this is only one configuration of having the first row, second row, and the third row. I can also have the first row, second row, third row. No, it's not times 5, Alexandra. That times 5 is only because even has only one position. Like you have 5 positions for even. Even can be in 5 different places. There's only one even number. This one is a little bit different because I have 3 of those. I want them to be 1 or 2. So I don't know if you guys see that. That the number of ways that I can rearrange this is 5 choose 3. There's 5 choose 3 ways to select 3 of the 5 roles to be a 1 or a 2. I know you say, wait, but you say order doesn't, combination means order doesn't matter, but we care about the order, right? But think about what I'm counting. I'm counting how many ways to select these to be A's. So how many ways are there? Right? I just want to find how many ways can I get? 3 of the 5. I want to select 3 of the 5. I don't care so much about, so this becomes like 1, 2, 3, 4, 5. This becomes like how many ways can I select? Of those 5, I want 3 of them. So this is one of the ways. 1, 2, and 4, that's one way. But then I can also use 2, 3, 5. That's another way. 5 choose 3 counts all those ways. So 5 choose 3 is what? I believe it's 10, isn't it? 5 times 4. It's 10. There's 10 of these. I can rearrange this 10 different ways. So this number is going to be what? What's the probability? The total probability then? The probability of rolling a 1 or a 2 exactly 3 out of 5 rolls is 10 multiplied by 4 over 243, which is 40 out of 243. Does that make sense? If you have a question about this, please let me know. This is very crucial. If you're able to understand this, it's very important. So do you see how here I could have said, instead of doing like, because this number is so small, it doesn't matter, but I can say of these 5 choices, I want one of them to be odd. So how many ways is that? 5 choose 1, which is 5. You see how that's consistent? So same thing here. Of these 5 spots, I want 3 of them to be event 1 or 2 happening, which is 5 choose 3 ways, which is 10. Okay. Okay, so to finish this off, let's look at part C. Hopefully everything comes full circle with part C. Part C says we get a 6. We roll a 6 in at most, at most 2 of the rolls. So here we have to be a little bit more careful. So the idea here is that at most, if you deal with complementary counting here, it's actually more work. So complementary counting it's not always the convenient way. In this case, it would be more work if I do the complement of this. It's actually less work if I go directly at most 2. What does at most 2 mean? It means you can have 0, you can have 1, or you can have 2 of the rolls being 6s. So here, the best way is actually case work. Case number 1, I have 0 I have 0 sixes. So first of all, what does it mean to roll a 6? What's the probability of rolling a 6? 1/6, right? What's the probability of not getting a 6? 5/6. So then what's the probability of me getting 0 sixes? Well, that's if I get everything that's not a 6. So if I get not a 6, what's the probability of getting not a 6 of the of the 5 times, right? Of the 5 times, right? Exactly, Oliver. Very good. 5/6 to the 5th power. That's the probability. And that's a pretty big number, right? 6, that's like what, 5 to the 5th power? It's pretty big. It's 3125. This would be 6 to the 5th, which is 7776. That would be the probability of me rolling 5 of those rolls are not 6s. Now that's case 1. Case 2 is if I got 1 being a 6. Well, what's the probability of me getting 1/6? That's a 6. What's the probability of me getting not a 6? 5/6. But I have, instead of, I want one of them to be a 6, so then the other 4 have to be non-6s. So the 4th power, 5/6 is raised to the 4th power. And of those 5 rolls, I want one of them to be a 6. So that's 5 choose 1 ways of selecting it. So that'll be another 5 here. So this actually would be 5 to the 5th power over 6 to the 5th power. It'll be the same thing as the above. 3125 over 7776. And then lastly, hold on. Lastly, case 3. What does case 3 say? I want 2 6s. So 2 6s out of the 5, right? 1, 2, 3, 4, 5. I want 2 6s. To get 2 6s, I must have 1/6 squared, because if this is a 6, this is a 6, I have 1/2 of that chance, 1/6 of that chance happening, 1/6 of that happening. And the rest of them have to be non-6s. So this is 5/6 cubed. And then the question is, how many ways can I have the 6 appear? I can have it in the 2nd row, and in the 4th row. I can have it in the 1st row, last row. How many ways do I do that? I do 15 choose 2, I use 5 choose 2 ways, right? There's 5 choose 2 ways of selecting 2 of them out of the 5, right? So don't forget what this 5 choose 2 means. This is the number of ways of selecting 2 rows to be 2 rows out of the 5. Out of the 5 rows to be a 6. And 5 choose 2 is 15. So this should be 15 times 5, which is 125, over 6 to the 5th power. So 125 times 15, that's 1875 over 7776. And so because all these cases are mutually exclusive, you add them all up together to find the total probability. So what's the total probability of rolling a 6 at most 2 times? It's going to be 3125 over 7776 plus 3125 over 7776 plus 1875 over 7776. So if you do that, what happens? 3125. One. So something's up here. Hold on one sec. We got a 6 and at most 2 of the rows. The 5 rows, right? There's 5 rows, yes. And then we want 0 6s. 3 1 2 5 3 5 6 2 6s. Yeah, so the problem here is that this number is bigger than 1, which is no good. So there's something wrong. We get a 6 and at most 2 of the rows. Hmm. Do you guys see anything that I may have looked over, glossed over? Sometimes going too fast, that's what happens. There might be a little tiny thing that I don't see at the moment. Right now, so let's go back and forth. Okay, let's go back. 5 choose 2 is 10. Is that what it is? Thank you. Why did I say 15? I saw Chitanya. I'm like, yeah, this must be 15. Thank you. Thank you. You saved my life. All right, this is 10. 5 choose 2 is 10. What am I talking about? That's extra. Oh man, why do I do this? Why? It's like the little tiny things, you see, like, oh my god. Okay, so this is not 1875 because that'll be too much. It's 1250. You see, it's one little thing like that. So Chaitanya, please be careful with that. Okay, five. Oh, what is it? What's 15? Isn't it like 5 choose 3, right? Oh, believe me. Oh, 6 choose 2. Ah, that's what it was. Yeah, 6 choose 2 is 15. That's right. That's right. It's okay. We're all learning here. I'm learning too. Believe me, Alexandra, if you're talking about anyone that makes mistakes, is the guy up here. This guy right here. I've made more mistakes than all of you. So in a way, that's how you learn, you know? It's like you learn through mistakes. Like the more you're able to figure them out, the more you're able to figure out your own mistakes, the better you become at whatever it is. Andre 3000. Yeah. Well, I am not a god, nor not even close to a math god. No way, no shape or form. I just, I feel like I'm a human, and I'm showing you the human side of mathematics. You know what? That's what I'm trying to do. I'm trying to show everybody the human side, because people look at people that do math and they think that, oh, we're like so, like, oh wow, they know so much, but really, no, we're just like you guys. We just have done more over the past. We've done more of math than you may have. Then that's true. But so this number reduces to 625 over 648, which is the correct answer. You guys see that? But again, you see, that's why I was also like perplexed. I was like, wait, we did everything correct. It's just one miscalculation. That was it. The order of things, the organization matters. Okay, as long as that's set, then the little calculation errors, you can find that and fix that really quick. You can change that really quick, as we just did. 10, then that just works out so perfectly. The moment this became a 15, I'm way over 7,000. So I'm like, wait, something's wrong. I must have made one little arithmetic mistake, and I did. So thank you for catching that. Zuze, is that what it is? Sorry if I said your name wrong. Zuze. Thank you. Okay, anything else? Anything else? Anything at all? So much to choose from, right? I mean, we can stop here if it's okay, no problem. No problem. This is really for you guys. If you guys like understand what's going on, if I went too fast, just let me know. If you want to, me look over a step that I did, Can we go over one question, chapter 4? Yeah, but you have to tell me which one, Oliver. There's many to choose from. And 3.4, number 1. So the 3 cards are chosen at random from a standard deck. What's the probability that they're not all the same color? So let's do that, and then let's do chapter 4, and then we'll call it a day, okay? All right, so let's do 3.4, number 1. So 3.4, number 1 says 3 cards are chosen at random from a 52 card deck, right? We love these problems, right? So we got 3 cards and we have a 52 card deck. And pardon me, it says, what's the probability that they are not all the same color? So the probability, not all the same color. Ding, 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 complementary, right? If they're not all the same color, what's the complement of not being all the same color? There are the same. So you have to do 1 minus the probability that they are the same, all the same color. I think that's a little easier to deal with than having different colors. You can do that directly as well, but this is a little bit easier. Now, in this probability, we have to consider 2 cases. Either they're all red or either they're all black. Those are the 2 different colors that we're just speaking of in a 52 card deck, right? You have the red suits, which are the hearts and the diamonds, and we have the black suits, which are the clubs and the spade. So then let's look at that. So the probability, all the same color, is the probability that they're what? All red or all black. Mutually exclusive, correct? So this is the same thing saying the probability of all red plus the probability of all black. What's the probability of getting all red cards? You can do this in more than one way. I rather use the combinations way. You could use permutations with the slots and all that, but I just think combinations is a bit more direct. How many red cards do I have? 26. How many do I choose from? 3. What's the total number of ways for me doing that? Well, there's 52 cards overall, and I choose 3. You see that? I don't have to worry about that to multiply by 3 factorial, not 3 factorial. I don't have to worry about that. Next, isn't that the same thing as all black by symmetry? It's the same thing, isn't it? So really, I have 2 of these guys. I have 2 of these guys. And of course, you use your calculator, but I just want to show you how the computation works out. This becomes we're doing combinations because does it really matter that I get 1, 2 of hearts, 1, 3 of diamonds, and 1 jack of hearts? Does it matter that I chose it that way, or if I chose 1 queen of diamonds, 1, I don't even know what I just said, but does it matter? It doesn't, right? It's the combination just says I want to select 3 of those red. That's it. So that's the number of ways of selecting me 3 of those 26 red. I can think about it as order does matter, but that's the thing. Do you want to do that? Be my guest. You have to worry about the permutations of things. I don't want to worry about that. I just want to get the number. So it's easier to deal with combinations in this case. So this becomes 26 times 25 times 24 times 23 factorial, 23 factorial times 3 factorial. The 23 factorials cancel. This is 52 times 51 times 50 over 49 factorial times 3 factorial times 49 factorial. 49 factorials cancel. And then when you see that the 3 factorials cancel up here, so this is what I'm going to get as a result. 2 times 26 times 25 times 24 all over 52 times 51 times 50. Again, this is not all necessary. I just want to write this stuff out so it can like give us a little bit more insight. But if you use your calculator times 226 times 25 times 24, 52 times 51 times 50, I get 4 over 17. When all is said and done, when you can cancel this out. You can do 26, this becomes 2, right? This becomes a 1. 25, this becomes a 2 here. The 2's cancel here, and then you get, this is 3 times 8 over 3 times, what was that again? 3, 17. 17 times 2. The 3's cancel, this 2, this becomes a 4. You get 4 over 17, regardless. So that's the probability of getting what? Same color. What's the probability of getting not all the same color? 1 minus 4 over 17, which equals 13 over 17. Done. Excellent, right? It feels good when things work out so nicely. Okay, and then last one, Oliver, did you select one? From chapter 4. There's 2 kinds. There's the conditional probability selection that you want, that you can get, or the Bayes formula stuff. 4.2, last question, looks rough. Let's see how rough it looks like. Just because it's long doesn't mean that it's hard, like in terms of the difficulty. Just because you see a large passage, it doesn't mean. I have a question about typo in 4.1 number 2. Is there a typo? There could be. 4.1.
Part C and the given values are the same. I think one is supposed to be an intersection instead of a unison.
Say it one more time.
Number 2, 4.1,
Yeah.
the given value of the E unison F, and then question part C is the same E unison F. What's the answer? But they give it to you in the question. So I'm wondering if either C or the given value in the question are supposed to be an intersection instead of a unison.
Let me. Could be a little typo. Could be. That happens. Probability. Oh, I see what you're saying. Yeah, you're right. I give you the answer, and I'm asking you for yeah. That meant to be an intersection. You're right. So I'll make that correction and upload it. You're right. You're right. So part C, there's a typo. It should not be a union symbol. It should be an intersection symbol, because that wouldn't make much sense if I give you the answer in the question itself. So. Oh, is there, Oliver? Thank you for letting me know. I have no idea. I have no idea how the people without a QCID enter in. Can you come before 8 a.m.? Well, I definitely would suggest to do so. You heard the college is closed. Yeah, I don't know why they would have it closed if you have 8 a.m. classes. That is very strange. Yeah. I feel like they should to tell you the truth, I have no idea how it's gonna look tomorrow, guys. I have no idea. This is the first time we've ever had something like this ever. So I think we're all gonna learn through this. So I just think about all the people that may have exams tomorrow, and all the people that have to wait to get in, and the checking of things. Yeah, it's gonna be kind of interesting. Very interesting. 3 exams tomorrow. Wow. So yeah, I guess there's gonna be a lot of people. I feel like a lot of people are gonna be there tomorrow, guys. Because I think a lot of people are doing the same thing. They're giving an exam tomorrow. Yeah. So be early. I think that's the best thing. Yeah, be as early as possible. And I'll understand about the scenario of how things are, because it should let people in though. They should, but I'm not sure about that. I'm not. All right, so 4.2 number 5, is that it? Is that the one, Oliver? 4.2 number 5? Yeah, and Rathis Hall, where we're gonna be, I'll show you from the campus map. It's not too far from the main boulevard, the Casena Boulevard. It's not too far from the main entrance. So if you're able to go to the main entrance, Rathis should be okay. Like the other places, like that are more like inland within the campus, you may have to walk more for that. But for Rathis, you shouldn't be much of a walk from the main entrance. But anyways, number 5, there's 3 different machines, M1, M2, M3. Suppose that 20% of the items are produced by M1, 30% by M2, and 50% by M3. Suppose that 1% of the items from M1 are defective, 2% from M2 are defective, and 3% from M3 are defective. You see, this is just like really long in terms of the information, but if you look at the problem itself, the structure of this problem is identical to the one we did in class with the different urns. And it's similar with number 3 and number 4. Like the structure of the problems are all identical. Yeah, it's number 5 is the same structurally as number 2, 3, and 4. They're the same problems. It's just a different scenario and different numbers per percentages, but the structure of the problem is exactly the same. Because it's the same and it's the Bayes formula, the way to consider this is using the tree diagram. That's like the easiest thing to think about, and hopefully things clear up like this. So either the items are produced from these 3 machines, and there's percentages for each machine being produced from that machine. There's 20%, right? 0.20 comes from M1, 0.30 comes from M2, and half of them come from M3. Done already with half of it. So then now M1, I can either have defective or non-defective. So I'm gonna write this as N and D. So either have non-defective machines or defective machines. I either have non-defective machines or defective machines from machine 2. I have non-defective machines or defective machines from machine 3. And then it tells me what's the percentage of the items being defective from machine 1. It's 0.01 because 1% is 0.01. So this should be 0.99. Then defective from machine 2 is 2%. Oh, wow. So nice. This is 0.98. Then this is 0.97, and this is 0.03. That's it, guys. Wow, we did it. If you have this, you have the problem in the back of your head. And then it says, suppose that one item is selected at random from the entire batch and is found to be defective. What are the defective ones? Defective, defective, defective. So then it's all of this, with all of this, with all of this. These are all the defective ones. And the one that I care about is machine 2. So I really care about this one. I want this occurrence to happen. I want this probability of this occurrence. So I want to find what is the probability of this occurrence happening out of all the different occurrences of it being defective. That's it. That's Bayes' formula in a nutshell. Bayes' formula. So the probability that it's defective, that is from machine 2, given that it's defective, it's the same thing as saying what? The probability that it's that it's defective coming from machine 2, the probability that it is from machine 2, all over the probability that it's defective, given that it's machine 1, multiplied by probability is machine 1, plus the probability that's defective, given that it's machine 2, multiplied by probability of machine 2, plus the probability that it's defective, given that it's machine 3, multiplied by probability of machine 3. Which is saying, hey, multiply 0.02 by 0.30. This is 0.01 multiplied by 0.20 plus 0.02 multiplied by 0.30 plus 0.03 multiplied by 0.50. Put this in your calculator and you should get the correct answer. So you put this in your calculator. I'll put that in mine. So you get 0.02 times 0.3, 0.01 times 0.2 plus 0.02 times 0.3 plus 0.03 times 0.5. And I get math enter, and I get 6/23, which is approximately 2.6. Yeah, it's approximately 0.26. So the answer that you see in the answer that you see in the answer sheet is an approximation. So I would rather you give me the fraction. That's the exact value, not 0. If I say rounded to the nearest 2 decimal places, then you put 0.26. But if I don't specify, then I'm assuming that you're writing it in the exact form, which would be the fraction 6/23. But again, this problem, number 5, is the same as number 4, number 3, and number 2, because you're dealing with 3 different scenarios, and for each scenario, you have 2 different outcomes. Any questions? Good luck. So I'll stop with the recording here.